Thank you. Hello, everybody. Again, I'm very glad to see also persons who I know. And thank you for invitation. I am going to talk about derivations in group algebras first of all, and about an approach to how to calculate derivations and other look-like families of operators. First of all, if you have got any questions, you can, of course, answer at any moment, or you can write to chat. I see it on my second monitor. So let us start. First of all, most part of my talk is about operators on group algebras, but in fact, this talk can be also generalized to some other structures, and I will talk about that at the end of my speak. Just to remind you that a group algebra is the space of finite linear combinations which look like this one. Of course, it is a ring. Of course, it is an algebra. Of course, you can take these coefficients not from complex numbers, but also from other fields or rings. And another type of interesting cases, I will talk about that a little bit at the end of my speak. Also, when I will talk about some examples and some generalizations of this construction. So but this will be at the end of my talk. Very common definition. What is a derivation? Derivation is a linear operator that satisfies to the Leibniz rule. So it is written here. Here it is, and of course you can write it some other rules which look like Leibniz. For example, you can write something like this, plus, for example, tau of U, that we here sigma and tau are some endomorphisms in a group. But you can also write, you can add grading structure to this. If you have got if you have got a structure of graded algebra on group algebra, then you can consider so-called graded derivations. It is also the construction which is near to the main goal of my talk. But we will take Leibniz rule because it is the most easy case. And again, I will say that you can generalize this construction to some other cases, and this will be talked at the end. And my main goal is to give you a way, an instrument to describe all derivations. First of all, you have got so-called inner derivations, which are written here. Of course, it is easy to check that this is a derivation because this is a linear operator, and the Leibniz rule is just a calculation that it holds for such type of operators. That's first of all. Secondary, the main question, very well-known question, is the so-called Johnson's problem. Is there any other derivations except of inner? So, because inner derivations form an ideal in algebra fold derivations, then outer derivations are factor algebra, quotient algebra by inner derivations. First of all, very well known result of Johnson that if you take a Banach bimodal over group algebra, then there are no outer derivations. All derivations are inner if and only if the group J is emanable. Another question, which was solved by Victor Lazare in 2008 year, is that all derivations in L1 over G are inner. It's a result of Lazare. It's also well known. It was published in Annals of Mathematics. And there are a lot of other papers in which they're talking about some different types of algebras and prove that there are no outer derivations. All derivations are inner. For example, you can find such results for Neumann algebras and in some other cases. Another point is that if you are considering derivations with finite coefficients, so you take as a coefficients elements from a finite ring, for example, then you can easily find that there are a lot of derivations which are not inner. Such results, for example, were published by Bavdi and others. And another question, and when we started with Professor Mischchenko investigating this problem, we found out that for common group algebras, there are outer derivations, and they have got a very easy, you can find examples in a very easy way. For example, we call them central derivations, operators which are given by this formula here. Z is element of from a group, so that it commutates with all elements of the group, and tau is a homomorphism. So tau of AB is sum of tau of A and tau of B. It's rather easy calculation that this operator is a derivation. And for the first time, we thought that there are some problems with Lozo's theorem and with Johnson's hypothesis. But then we saw that this is a problem of topological structure in the group algebra. So if you take a group algebra, you get there some kind of topological structure. For example, you give a norm there, and you look on it as on a Banach space. So then derivations which are not inner, for example, central derivations, turn to be not bounded. So that's why that happens. But first of all, we will talk about group algebras, and I will give a construction how to find out such derivations, and what is our plan? What is the method about which I'm talking about? First of all, you take a group algebra, then you construct a groupoid which is associated with inner action of a group on itself. It's a groupoid of a joint action. Then you find on it some characters. It's some specific functions, and these functions, they describe derivations. So inner derivations, for example, it's one class of such characters. Central derivations are another class of such characters, and you have to find out if you have any other characters except of these two types. So this is a plan. This is a main method. Is so again, you take a group algebra, you take or any other algebra, you construct with the help of each groupoid, then you look for characters, and these characters describe your derivations or not derivations. If you take other types of groupoids, then you will get, for example, Fox derivatives or group characters or sigma tau derivations and other different cases of generalization of this idea. So this is the plan. Now I'm going to talk you how to realize it. First of all, we have to construct the groupoid. So groupoid has got objects or points in geometric way, and each have got, so this is points, this is arrows. The arrow on which is labeled by letters U and V goes from V minus U to U V inverted. And the composition is written, can be defined by formula 2. So it means the following. If you have got here one morphism, then you have got second morphism. Of course, you need that source of the second morphism is equal to the target of the previous morphism. Such morphisms are called composable, and you write a composition. So this formula must be written on this arrow. I think it's rather geometric, and it's not a problem to understand this definition. Of course, you have to check that this composition formula is associative. You must find out that there, for each arrow, you can find an inverted arrow, which goes in the backside, such that their composition is a neutral arrow, so that you can just calculate that. For example, neutral arrow is written like this, J and then neutral element of a group. So this is with help of these ideas, you can prove that this that gamma, which is defined like this, is a groupoid. So all arrows can be inverted. There's composition is associative. So this is a groupoid. It's very important to understand how this groupoid looks like. And it's rather easy to see that you have got an arrow between A and B just if they are conjugated in a group. So this is why this groupoid is very near the joint action. Now we can define characters of this groupoid. So as I told a little bit before, it's just a function on morphisms, on arrows. So if you have got two composable arrows, for example, like here, C and phi, and you write here number alpha, here number beta, then on the composition you must write alpha plus beta. So this means what? This is alpha, this is beta, and this is alpha plus beta. So if you have got a composition on arrows, it's very the first idea is to write some numbers on the arrows and to summarize them if you have got a composition between the two arrows. So the main here theorem is this one, that each derivation can be represented as a character. So for each derivation, there exists a character such that formula 5, write a number here, such that formula 5 holds. And in another way, if you have got a character and each is a so-called local affinity character, that means that it is trivial for each v, it is trivial for almost all u. That means locally finite. Then such a character describes a derivation. Where are we taking this a little bit strange condition of local finiteness? Because it is a condition of that your mapping goes to the group algebra. So the sum in the image is finite. So what is the geometric look on this? This part of the composition condition gives you Leibniz rule. And this part, locally finite, is equal to that your image is in a group algebra. So if you take some other condition, no, like Leibniz rule, then you must check another groupoid. So if you check another groupoid, then the composition there and the corresponding formula for characters will give you another Leibniz look-like rule. That's the main idea. So you are changing groupoid, then you are changing Leibniz rule. So twisting that or something like that. And if you change the space of characters which you can take, then you are changing the image, the area where you're working. So if you take not a group algebra but some Banach bimodule, then you must change local affinities to something else. How to work with characters? It is a very useful instrument, so-called conjugacy diagrams. So I will define them for my groupoid, but also you can take very similar definition for other types of action. And if you remember what is Cayley graph, then it looks like a Cayley graph of a group. If I have to say what is the Cayley graph, I can tell it, but please let me know about it. So the definition of conjugacy diagram. If you take two elements in a group, A and B, and then you have got an arrow between them, which is labeled by letter X, it means that B is X minus 1. So, for example, for Cayley graphs, you have got very similar. You have got a label X. Let's write that it's a Cayley graph. If AX is equal to B. So here you have got action of left translations. Here you have got an action of conjugacy. This is a definition of conjugacy diagrams, and the main lemma about them is the following: that if you have got conjugacy diagram and you have got character on it, character on them defines in the following in common way. So if you have got a character on conjugacy diagram, then it can be extended to a character on a groupoid. And so to find out characters on conjugacy diagrams, each is equal to find characters on a groupoid, and each is equal to find all derivations. So this is the logical way. And on each iteration of it way, we make our problem more easy and more geometrical. I'm sorry. Several words about geometry of such diagrams. Of course, if you take different generating sets, you will get different graphs, of course. But they are different, but they are coarsely equivalent, as we say. Or you have got a quasi-isometry between them. So what is the quasi-isometry? If you have got two metric spaces, and the map f between them, then if this long equation holds, this long formula holds, then there are then map f is called coarse map, and if the second holds, then it is called quasi-isometry. So what does this mean? This means if you take in the space M another M1, another space M2, and you have got 2 points in M1, then their images are not very far from each other. They are controllable. The 2 points which were far away, they will be again far away, but not very far. This is a geometrical view of it. And my idea is that all such conjugacy diagrams or diagrams of other types of action are coarsely equivalent. So they are not isometrical to each other, but they are coarsely equivalent. And so some nice pictures. For example, if you take, this is a conjugacy diagram for Heisenberg group. So it is the group of unit triangle matrices. So you can see that it is coarsely equivalent to the real line. And for example, for free groups, I'll make it a little bit nearer. So you can see that you have got rectangle in the here and trees which grows from this rectangle. It's the case of nilpotent groups. So if you take another element in a free group, then you have that it will look like something here, and trees which grow from it, so on. And here on the diagram, it is written the word which generates the centralizer of it, because centralizers in free groups are cyclic, so on. And here it's a little bit more nice picture. It's the case of so-called Baumschlag solitary group. Baumschlag solitary group is the group of which has a co-representation Mn, such a co-representation, and this is example that this graph conjugacy diagram is not vertex transitive. So you can see here that it is not vertex transitive, and it because why I'm talking about it, because Cayley graphs are vertex transitive, and as you see from this picture, conjugacy diagrams are not. So what's next? Next we have got now a language of characters, and we can prove that if a derivation is inner, then the corresponding character corresponding by a formula which was written here. I'm talking about this formula 5 again. So if the derivation is inner, then the corresponding character is trivial on loops, first of all. Secondary, there are derivations which are not inner, but which have a character which is trivial on loops. We will call such derivations quasi-inner derivations. So quasi-inner derivation is such a derivation that its character is trivial on loops. Of course, inner derivations are quasi-inner derivations, but not all quasi-inner derivations are inner. And this can be described by this theorem that for a subgroupoid gamma, you have to take its conjugacy diagram and calculate number of ends there. Then you will see that this is formula for quotient of quasi-inner derivations by inner derivations. For example, here you have got two ends. So you have got one-dimensioned space of quotient of quasi-inner derivations by inner derivations, and here you have got infinite many ends, and so you can find that there are a lot of infinitely dimensioned space of quasi-inner, not inner derivations. That's first of all. And another question is how to find out quasi-outer derivations. Because you can see that quasi-inner derivation, how it, what is the connection to inner derivation? If there is quasi-inner, then you can write a formal sum of DE where DE are inner. Because why this is a formal sum? Because this sum is not you cannot summarize this ray in the group algebra, but you can summarize it in the space of all bounded sequences, for example. That's first idea. And what is a quasi-outer derivation? Quasi-outer derivation is such a derivation that it is not trivial on loops. So, of course, quasi-outer derivations cannot coincide with inner derivations. That's first of all. And secondary, they cannot be written in such a form. So, go looking backward to our definitions, central derivation can be presented by a character of the following view. You have got a subgroupoid with one object Z, the element of center, and what was written on loops, it's what we have to write from that formula. So central derivation is not trivial on loops, so it cannot coincide with inner derivation. And another theorem which I must note, that quasi-inner derivations form an ideal. So the quasi-outer derivations are also a quotient subalgebra when you take a quotient by quasi-inner derivations. So it's and the classical decomposition is following. You take all derivations, you find the ideal of inner derivations, and you take a quotient by them. I told to you that here is another view. You can take an algebra of all derivations. You take an ideal of quasi-inner derivations, which in generalize don't coincide with inner derivations, and you can take a factor by them, which will be quasi-outer derivations. And for example, result of Johnson, which I mentioned, is that in L1, all derivations are inner if J is ebenable. Looking here, that means the following. If all derivations, if J isn't ebenable, then all derivations are quasi-inner. They cannot be quasi-outer. I will prove that a little bit later. So this means that, for example, Johnson, in fact, calculated the space, this space of quasi-inner by quotient by inner derivations, but he didn't know about that. So again, about my idea of another inductive identities, which I told about before. If you take any group action on itself, not, for example, not a conjugacy, then you can define the following family of operators, and each operator which acts on a group algebra and satisfies the identity 7 can be written with the help of character here on the corresponding action groupoid by formula 8. Of course, identity in view of formula 7 looks like very strange, but we can take two examples. First of them is action of conjugations. Then you take classical Leibniz rule, and if you take the action of shifts of translation, left translations, then the corresponding graph is a Cayley graph, and you will get such analog of Leibniz rule, and it's also called Fox derivations, Fox derivatives, I'm sorry. They were investigated by Fox for not calculating, and they're rather famous, as I know. I think that you can find out also other examples, but I didn't find such other interesting families of inductive identities, but except of one, sigma tau derivations, but I'll talk about them a little bit later. So here's the theorem which was proved with me and my student Lev Kosolapov. We decided to take coefficients not from complex numbers, but from unital commutative ring. Then you can find out how look like derivations. You can find out when they are all trivial. I'm sorry, when they are all inner or not, and so on. And I must I'm sorry, I have to note that such derivations were studied by Hages, Krividen, and some others in the cryptography context. And so I think that for applications, these results will be useful. I believe that. Now, another problem, it's so-called twisted derivations or sigma tau derivations. Here results from common paper with my student Alexander Alexeyev and Professor Sergei Silvestrov. We looked out for derivations which satisfy to such identity. Here, sigma and tau are endomorphisms from a group, which are extended from a group endomorphisms. And then the similar idea, you have to take you have to consider a twisted groupoid, objects, arrows, the composition. You see, this is a twisted composition also. And also all sigma tau derivations can be defined, can be investigated as the functions which are generated by the corresponding characters. That's the characters on the twisted groupoid. And what I was talking several minutes before, if you take the Banach bimodule, for example, you take a norm which is subordinated to the supremum norma, then all derivations are inner. I'm sorry, not inner, but that all derivations are quasi-inner. Why? Because if you take a loop and it is written something not equal to 0, then you can take a composition of each loop with itself infinitely times, and you will have got the corresponding character tends to infinity. And this is in fact all the proof. And again, for example, Johnson proved that for amenable groups, all derivations are inner. And if the derivation, if the group is not amenable, then the corresponding group algebra derivations are not inner. So we prove very similar thing, that if you take all derivations, they are quasi-inner everywhere, always. You cannot find out an example of quasi-outer derivations. But if you take norms which are not subordinated to supremum norm, then you can find such derivations. Its results from me and my student Alexei Nayanzin, and we considered such norms, which, of course, they are not subordinated to supremum norma. And then in such norms, all central derivations, for example, are bounded, not just Leibniz. So I want to say again, what is the idea? If you want to calculate how looks like operators which satisfy to some Leibniz-like condition, then you have to take an groupoid, then you have to take characters on its groupoid, and then you have to take the diagram, and on this diagram will give you a lot of information about how that derivations or other operators, I don't know how you would like to call them, how they look like. For example, you can find inner derivations, quasi-inner derivations, outer, quasi-outer derivations, and so on. For example, for the case of sigma tau derivations, we proved that all derivations in finite group are inner. It looks like easy theorem because it's well known for classical group algebras. But for example, for sigma tau derivations, that result was opened just in several years before us by Indian mathematician Chaudhuri, and so on. So each is a good language and good combinatorial way to calculate such derivations. Except of all these derivations are very nice. For example, this is a diagram which was found by my student Ilya Bobrov. It is a diagram in S6 group. You can download this presentation, and you can look my other papers, which are almost all of them are in ResearchGate, and some of links to them is here, and I will finish, I think, right now. Thank you. I will be very glad to answer your questions.
Thank you very much. Are there questions?
Excuse me?
Thank you very much. I'm asking whether there are questions.
Okay.
May I ask a question? Sergey Sylvester from Sweden. Unfortunately, my video is not working, but
Hello, sir. Very nice
yeah,
to
hello,
see
hello, hello, Andronick. Yes, I just have simple question. This Fox derivations, isn't it? It's just a very special case of sigma tau derivations, right? Because if
yes.
you take one of the maps, just identical map, trivial map to
Yes, Sergey, of course, but it was I considered them as a special case because there are a lot of people who knows about Fox derivatives and don't know about sigma tau derivations. There's people who work with knots, and it's
yeah. Now I understand where this Fox derivations.
Yes, but of course it is the case of sigma tau derivations. You're right.
Yeah, right. Okay, thanks.
Thank you. Other questions? So if not, we thank Andronick once again for his nice presentation. So, and wish you all a nice week. So see you later.
Thank you. Thank you very much. See you.
See you.